We are welcome today to the class. So as we promised, inshallah, we're starting off with ensemble methods. So what do we mean by ensemble methods? Ensemble is a kind of model combination in a special way. So we want to see, sometimes we're working with individual model. You keep trying all what we've discussed. You have done data pre-processing. You clean the noise. In fact, you did normalization. You went into carrying out feature selection, trying different partitions, cross-validation. You try all sorts of things, fixing the missing data, trying to locate the outliers and try to fix them. But still, with all these efforts, sometimes you could still get stuck with less than what you are expecting. So at that point, what do? You have changed from one model to the other. You have tried virtually all the algorithms that you are aware of as individuals. So maybe it could be time for you to start looking elsewhere by trying to say, okay, can we combine? That is, as we know, it's kind of effort, but let's have a combination of effort. You look at it, I look at it, then we come together and discuss. I used to compare it to the classical Jama, a group. It is established for that group work is always better than individual. And then they used to say that two good heads, it used to be two heads are better than one. But sometimes someone told me it's not just two heads, it's two good heads. If you agree with that, whichever version, it's established for that when you have a group of people that get together to solve a particular problem, they're likely going to solve it better than an individual, no matter the level of his expertise. In as much as those people also, they are not just random person, they are also experts in the same field. Because that point has to be clear. They are also experts in the same field, but now they combine the idea to solve a particular problem. Most likely, with high probability, they are likely going to get it better. So this is the idea of ensemble methods. That sometimes individual models might not be able to scale up to your expectation in a particular field of application. So you don't give up, rather you proceed to try to go for what we call ensemble methods. Now, so inshallah, we're going to be looking into introduction and preambles, some of the success stories about ensemble method that made it to be very convincing to try, because there are challenges with it. It has computational complexity, because you are going to, instead of running one model now, you have to run like several models and then combine their results. So if it doesn't really worth it, there's no point going for it, actually, because you are going to waste a lot of effort doing that. But then if it really pays off at the end of the day, then you know why you are actually doing that. So we are going to look into real-life practical examples that really show the uniqueness of ensemble, the generic method of generating base learners, review of sampling techniques. We're going to need sampling techniques. How do you resample your data when you want to build ensemble? How do we build ensemble? What are the methods that are available? Why do you use it? In what situation do you use it? Why do you need to use ensemble? And when do you use it? You need to be able to answer those basic questions so that you don't waste time doing such a thing. Different types, then stacking, which is one of the very recent methods in it that are getting popularity now. So, and then of course, everything with advantage also has its own disadvantages. Now, moving forward, said, why does ensemble work? So we want to look at it mathematically. So apology to the professors of maths here. So suppose there are 25 base learners and each classifier has an error rate of 0.35. So we assume that classifiers are independent, that the classifiers are independent of one another or of each other. So the probability that the ensemble classifier makes a wrong prediction is given by this mathematical outing. So which, as we can see, So we can see how the ensemble system is able to reduce the possibility of having an error from 0.35 down to 0.6. Yeah. So this is a kind of a mathematical way of showing that we can prove that. So that, okay, it can take it down to as low as 0.06. So rather than having 0.35 error for each of them, if we can bring it down by combining a couple of algorithms, maybe it's worth it. So why not give it a try? Now, furthermore, suppose that somebody is a patient with a set of symptoms. So instead of taking the opinion of one doctor, so this time around now we're going to consider a doctor like we're going to consider the medical doctor as a classifier now. So you are going to consider the medical doctor as a classifier. Now, so you decide to take opinion of a few doctors, or you get started with just only one doctor telling you, okay, this is what you have. So which one is better? Taking opinion of one doctor or decide to take opinion of several doctors? For sure, is this a good idea? We all agree it is better actually. So rather than just asking a medical doctor what's his opinion about these symptoms, and then you go out with whatever you recommend, everybody want to, okay, let me give it a try. Let me see what other doctors will say. So after trying a couple of doctors, then you say, oh, all of them are saying the same thing. Okay, maybe they are correct. So this is a real life kind of example of what we mean by ensemble. You want to take advantage of different opinions. Hopefully you can arrive at the best possible solution, hopefully. Now, so let's say after consulting them, so you consult many doctors, and based on their diagnosis, you get a fairly accurate idea of the diagnosis. So after consulting the doctors, there are two things that are involved. How do I take my decision? The first one is known as bargaining, majority voting, and that is democracy. Majority voting. We don't care about the expertise of those doctors. There's one doctor with maybe 50 years of experience or 45 years of experience. He's a professor of medicine, by the way, with so many experiences. But as a young doctor who just graduated last year, everybody has one vote. One vote. This is called bargaining. So you bag the outcome of their opinions. So if there are 21 doctors, you count them. How many people say go for surgery? How many people say don't go for surgery? So you go for the majority. That is bargaining. However, in real life situation, in some problems, we may find out that that might not work. So, because majority doesn't really mean they are correct. Maybe one professor is more experienced. So we go for the second option, which we call boosting. So in boosting, to me, it makes a very big sense in that we are going to try and boost. We try and boost a kind of the medical doctor that we so much trust his opinion. Perhaps maybe he's a full professor of medicine with several years of experiences. We think that we should consider him. If you say yes for something, we think this professor will not make a mistake. So we're going to give him more votes. We said, any vote from that professor, so it's going to be 3 votes. When that professor say yes, it is 3. So in that case, so we in the boosting option, so let's say we have Professor A, Professor P1, we give him, okay, 3 votes. There's another professor also with another 2 years of experience, we give him 2. And there's a young professor called P3, He just graduated. No, he's just a medical doctor, just graduated not long ago. We give him 1. So when these guys say yes, it's yes is times 3. When this one say yes, its own yes is times 2. And this one, if you say yes or no, its own is times 1. So in that case, if you have a situation whereby these guys, maybe this man says, this one said no. He said no. Professor say yes. And this one say no also. So we are going to have a kind of tie. You're into trouble. So in that case, we have to need more doctor to decide. But let's say, okay, this one also say yes. So that's going to be 3 plus 1. That's going to be 4 against 2. 4 against 2. And let's say we have only this professor. We have P1. And there are other doctors. Ordinary doctor, D1, D2. This is 1. This is 1. So this professor say, no, don't go with that surgery. And this guy say, you can go. You can go. Even though there are 2, we are going to go for this pro before he has 3 against 2. This is called boosting when it comes to ensemble system. So we try to boost the one we think is more experienced. And how do you do that in your own classifier? When you train a classifier, the classifier with highest accuracy, maybe one is getting 98% accuracy, another one is getting 65 or 75. So we can give this one more weight. Okay, whatever value you have, whatever voting, whatever answer you give, we're going to multiply by 0.5. Anything you get for you, we're going to multiply by 0.25 because we don't trust you like we trust this guy. You give more weight to the guy with the highest accuracy. This is called boosting. So it looks very interesting. However, it also has its own challenges, as we are going to see later as we move on. Because even though this professor is so well trusted because of his experience, it doesn't mean he cannot make a mistake. This is the problem of boosting as an ensemble combination method. So it means whenever he makes a mistake, we are going to be multiplying his mistake by 3. This is the problem with this boosting. If that professor, maybe he had a very bad family issue at home, or on the way coming, somebody hit his car. So he was at work that day, not in the complete state of mind or a troubled state of mind. He might make mistake in diagnosis. So it means whatever mistake he made that day, we are going to end up multiplying by 3 because we trusted him. So boosting also allows you to multiply the mistake of such trusted individual models. So because the fact that 98% here is very close to 100%, so we give it more, but it doesn't mean there is a mistake. It's making 2 mistakes out of 100. So whenever I made that mistake, we are going to be multiplying its mistake by 0.5 at the same time, or by 2, whatever value you are using. That is why this is one of the challenges of boosting. You can see bagging has a problem of ignoring expert opinion or expert experience. We round that to boosting. Boosting also has its own challenges. Then where do we go from there? We see as we proceed. See, that's why we have another one called stacking. Stacking tries to avoid this kind of problems of either boosting or bagging. So we'll come back to that one later on. But then bagging could work for you. You know, it depends on the kind of data. Always remember what I always tell us, let the data speak. Let the data speak. So you may use bagging for the problem you're solving now. It could work excellently fine. However, you may use the same bagging for another problem. It might not work. You can try boosting in that case. If none of them is working, then you can try the other guy, stacking, or you might have to do a kind of mixed mode, as we are going to also discuss later. So we say in bagging, you give equal weights to all classifiers, whereas in boosting, you give weighted according to the accuracy of the classifier. These are 2 very popular methods of combining classifiers in the ensemble system. Until recently, when the concept of stacking started coming in, so that, okay, we want to avoid the problem of boosting, we want to avoid the problem of bagging. So we are not going to count their votes, we are not going to multiply them, and we are not going to ignore the expert opinion. Rather, we will bring in another machine learning techniques, totally different, and use it to get us the final output. So we go into the detail of how that will happen later, inshallah. Now, what are the values of ensemble? We might try to practicalize this at our home, maybe different homes, and see how it works. I used to deal with my student in class. So when you're combining multiple independent and diverse decisions, each of which is at least more accurate than random guessing. So we say the random errors, we cancel each other out, and correct decisions are reinforced. These are established facts. Human ensemble are demonstrably better, actually. So how many jelly beans in the jar? Individual estimate versus group average. There are a lot of practical, real-life situations have been demonstrated in this case. So you have a jar with beans inside it. So if I ask one person to just tell me the estimation, or I ask all of you to estimate, and then we find the average of your estimation using bagging or using boosting, whatever you want to use. So you can demonstrate that in your classes or whatever, anywhere you want. You will see that group work always get better results. So who want to be a millionaire? So there's a very popular show. You see people saying, you want to be a millionaire? They ask a couple of questions. At the final stage, they'll give a particular question, and the participant has two options, either to ask the audience to vote for answer. Show your answer, yes or no. Or you want to consult an expert friend at home. There's a single friend at home that you have the opportunity to call that friend and ask him the question or her. What is the answer to this question? You only have one chance. Some people say, okay, let the audience vote for me. So from a lot of experience, they say the audience vote always give them better results, ensuring that they always win at the end of the day. Another popular one that is, what about having to identify your balloon in a class filled with many balloons on which names of owners were written? Do it individually or combine your efforts. So I used to do this regularly in my class, machine learning classes, until the coming of this pandemic. So what we do, we ask the student to bring balloon to the class. All of them must be the same color. So you need to write your name on that balloon. See, don't blow it, no need to blow it. Just write your name on the balloon. So your name is well written. This is Adam. And then we excuse everybody submit the balloon, we put it together. Then we try to shuffle it, and then we put it on the table. Okay, student, go there and pick your balloon. So you have to check each balloon one by one. It means every student, let me say we have like 200 students in that class. Every student must pick at least, for people are picking the 199 and not yet its own until you read that 200 before you pick your own. You keep checking, oh, this is not mine. Oh, this is not mine. Imagine the chaos. Imagine you have 1,000 students. Look at how long it's going to take them. But ensemble principle says, so we did this. This is the first experiment. The students struggle after some minutes. We give a timer. They check and they try to get their names, their balloon, each balloon out. It took a lot of time with a lot of chaotic scene. Then the second control experiment is, okay, drop back the balloon. And then we ask everybody to just go to that particular place, pick a balloon. You don't need to check if it is your balloon or not your balloon. Let us use our effort together, joint effort. Just pick a balloon, look at the name of the balloon on the balloon, look at the name written on the balloon, and announce it to people. Okay, oh, Adam, this is your balloon. You give it to the owner of the balloon. Within few minutes or few seconds, actually, depending on the size of the student, everybody got the balloon without any chaotic scene, without any trouble. Personally, I've practicalized with a couple of my students several sets and really demonstratively confirmed that ensemble techniques do work perfectly better than individual separate efforts. So these are some of the real life experience, real life practical cases that have really made ensemble to become very popular and made it very dear to me personally. When people suffer from bad classifiers, I usually encourage them to go into ensemble techniques and hopefully they get better results. Are you with me? Are we following?
Yes. Yes.
Okay. Yeah. Thank you. So that is ensemble in brief. So how ensemble works is, so you construct a set of classifier or models from training data, and then you predict the class label of previously unseen record by aggregating prediction made by multiple classifiers. So you train several classifiers using the training data. You train them separately. Then, during the prediction cases, we try to make them to predict. When they predict, then we aggregate their prediction and try to say, okay, what is this man saying? Out of 21, it's always good to, if you're going to go for voting, it's good to go for odd numbers so that you don't have a tie. We train like 15 classifiers. 7 of them saying yes, 8 of them saying no. So we go for no. You may have to train 155 classifiers. There's no limit to the number you can train. That's why I said that if there's no really need for it, don't go for it, because you need to expend a lot of energy. You cannot just train 3 classifiers for Ensemble and you say Ensemble is not good. No, if the data allows you 3 classifiers might be good to make an Ensemble, but in reality, you might have to train hundreds of classifiers. And then we bring all the results together and then let them vote or whatever option you use to combine the results. So this is a kind of a visualization of what we're saying. So we say an ensemble is a set of classifiers whose combined result give the final decision. You see, these are the features, the inputs. Small we can X1, X2, whatever. So we give it to classifier 1, we give it to classifier 2, we give it to classifier 3. So everybody will get trained. Then we use it then to do prediction. We have super classifier here. This is the ensemble guy, which can be bagging. It means you just can't vote. This one say yes, 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 sorry, no. So 2 of them say yes, 1 say no, we go for it. All of them also may say yes. It's not compulsory, they must contradict themselves. It gives you more confidence that you are correct, actually. All of them say yes, 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 that's okay. So this super classifier is that particular combiner. This is the combiner. It's not that will combine the result. You can use bagging, you can use boosting, and then you may have to use the stacking. In which case, this is going to be another classifier that will do the prediction for you. We'll talk about that one later. Now, so the general idea is you have the original training data. So you might need to create multiple data sets. We're going to that. There are different ways to build ensembles. So we have data set 1, data set 2, T-1 up to DT. Your T can be any number, 1001, 1022, 1010. I mean, it can be as big as possible. It can be as small as maybe 3, at least. So once you divide the data, then you cannot build multiple classifiers. This is classifier 1 build using this data. This data could all be the same thing if the classifier here are different. That's no problem. I'm using the same data. I kept it the same thing. And then I make sure that the classifier here, they are different. This is that case, we call it heterogeneous ensemble. Heterogeneous means we are using different classifiers to build the ensemble. But sometimes I want to use the same classifier, the same neural network all through. In that case, I need to make sure that the data that is coming in is different. It could just be by reshuffling them. It could be just by reshuffling the data. See, by partitioning into training and testing, the one that is part of the training is not part of testing next time, you partition again. And in some cases, it could be by even feature manipulation. In which case, I have like 500 features, 500 features, X1, X2, X3, up to X500. Imagine. In that case, I use X1 to X10 to build the first one. X1 to X10 will be here. X11 to X20 will be here. X21, I distribute those features like that. In fact, one of the places where, situation where you might be advised to use Ensemble, if the number of features are so high and you don't want to lose information in those features, then you can build Ensemble, build base classifier using a group of features, a group of features, a group of features. Let them now create classifier, and then those classifier, when new samples come in, use it to predict, and then you're going to have the super classifier here, which is the combiner that can use bagging, boosting, or stacking, as the case may be. This is a general idea, but so here, how do we make the data set? There are different ways to make the data set. We still talk about them, inshallah, in details. And then classifier also can be the same classifier and it could be different classifiers. And that makes it to be heterogeneous or homogeneous. If they are the same classifiers, homogeneous. If they are different classifiers, then become heterogeneous. So you can see, so when you break your data, you have the sample 1, sample 2, sample 3. So the base learner is another name for the initial classifier you are training. We train this base learner. It can be as many as possible, 1 up to M, you can see up to M. Now, this is model. And then we classify here. You see, this is the algorithm. This is the machine learning algorithm, which is the learner now, the one you want to train to learn. People ask, is there any difference between algorithm and model? I say, yes. See, it is when you train an algorithm by providing it with the data, the outcome is called a model. The outcome of that training is called a model. So the algorithm plus data in a process called training will lead to what we call model. So I've seen people trying to use algorithm synonymous with model. It's not the same. So we should get that right. So it is when you have trained an algorithm using the data that is available and using the training procedure you have selected, the outcome of that training is going to be the model you have produced. Now, so once we have the model from the outcome of these different data samples, then we have, you can see here also, the combiner also could be called the ballot box now. So when we have new test sample, okay, this guy say this sample coming in, I'm predicting it to be class 1, no, class yes, is diabetes, is not diabetes. How many do we have M? Our M is equal to maybe 3. If our M is 3 and 2 of them say yes, so this one is going to say the output is majority class. Yes, because we are using bagging. Also, we might use boosting, in which case there's some classifier there that if you say yes, your yes will be multiplied by 2 because your accuracy is very high. So whichever method we select. Now, we look at an example of majority vote for several linear models as an example. Let's look at it. Somebody built, this is just to demonstrate further how Ensemble works. So we have this kind of data in the plane, because this is negative classes, positive classes. Our target is to separate them into negative and positive. So we build the first model, linear model 1. Can you see that the linear model was able to separate these ones from this side? But then you can still see that in this side, we see a positive and negative. So only one linear model couldn't do the work. So we brought in another second one. This second model, this is model 1. This is model 2. It's able to do another one, separated positive here, but then you can still see negative is here, but positive and negative is still here. They are still together. Then we brought in M3. With M3, you can see totally, this one separated its own. You can now see that positive classes are now enclosed, and then all negative are already kicked out. This is to tell you that an ensemble can give you 100% separation into classes. What an individual model can never do. You can see how many percentage this one was able to do, how many percentage this one is able to do, how many percentage this one is able to do as individual. But when we combine them together, they were able to achieve 100%. This is the power of ensemble. See, and we all know that that is the power of togetherness. So when you are in a group, there's baraka, and you are most likely going to get things right. That is the idea of ensemble in real life. And we like to give a success story, a very popular one in this field. That is the Netflix. There was a case of $1 million prize. Then Netflix said they want people to come and improve the baseline movie recommendation approach of Netflix by 10% accuracy. That they want to recommend movie, so people should come and develop machine learning algorithm that can help them to improve their base, what they are using already, by just 10%. You increase it by 10%, you get the million, you get the number, the $1 million promise. So the top submissions all combine several teams and algorithm as an ensemble. Individual try, they never made it. See, we talked shortly about them. There are some also data mining competitions like KDD, classification problem. The winning teams always employ ensemble of classifier. They don't just go for the ensemble, but because the individual classifiers could not cope to that level. So let's talk more about the Netflix example. Netflix exam prize is a supervised learning task. It is, the training data is a set of users and ratings, 1, 2, 3, 4, 5 stars. You give rating to the movie. So you want to construct a classifier that given a user and an unrated movie, it can correctly classify that movie as either 1, 2, 3, or 5 stars. There is 1 million prize for a 10% improvement over the current movie recommended there. So people tried. People started and tried to get as many as possible. So you can see that at first, single models method are developed and performance are improved. The team started developing models. They improved the performance. However, improvements slowed down. At a point, the improvement didn't go up anymore. It gets stuck. You can face that in your application of machine learning, either in engineering, whatever area. You keep improving it by doing what we have discussed, feature selection. But at the point you just found out that I've tried several algorithms, it gets stuck. The same thing happened here. What later happened? Individuals and teams, they mark their results and significant improvement are observed. People realize that, look, this prize might go. Nobody will win this prize. They forgot about they are competing against themselves because these are teams from different countries. It's okay, you have achieved maybe 7%. They need 10% to win the prize. You achieve 6%. Let's bring all our algorithms together. So they brought all the outputs of their result and they merged them in an ensemble. And they were able to achieve that 10%. And then they can get their money and they can distribute among themselves. Again, telling us the power of unity. See, when you are united, you solve problem better. When you divided, even the best of you, you have a limitation you can cross. So I think that is a big message to everybody. So unity is always very, very important. That is the idea that Ensemble try to invigorate when you are using machine learning system. Another very popular real-life problem was the leaderboard competition. So people try a lot. So the final one that achieved the best concept of blending 107 individual results. This is what I want you all to know. It's not just 3 models only. 107. This is not, it's not a peanut. It's not easy to develop 107 models. They had to develop 107 individual models from where they were able to get the best result. And then there were recommendation suggestion for us. They said the predictive accuracy is substantially improved when blending multiple predictors. See, when you are blending multiple predictors, the experience is that most efforts should be concentrated in deriving substantially different approaches rather than refining a single technique. As an option when you are building Ensemble, you can try to refine neural network. I build first neural network. You can build first neural network 1 using maybe 2 layers. I build another ANN2, I use 3 layers. You can keep changing the number of layers, changing the topologies, changing many things. So you can build like 55 neural networks, but each of them are different in structure. But what they are saying here is based on experience, they don't encourage it, but you can do it. It depends on your data. They say rather than spending your time to develop 55 neural network, try to spend time, okay, you can develop like 15 neural network, develop another 15 support vector machine, another 15 k-nearest neighbor, try to mix different algorithms together. The idea is that the mistake that this algorithm is making, maybe another algorithm will not make it. Especially when we remember the concept of feature space. And I said that each algorithm has feature space where they operate. Hypothetic space, sorry. Yeah. This is SVM, and this is k-nearest neighbor. So these different feature spaces. So let them look at this problem from different angles now. And that is why when we want to blend, when you want to have an idea it's better for us to have an idea from people from different fields. When we're solving and that's why the world is encouraging multidisciplinary fields these days. We want people to come from different backgrounds. Let us see how they are going to look at the problem. Hopefully we can get better results. Now, so when you learn Ensemble, you learn multiple alternative definition of a concept using different training data or different learning algorithms, as the case may be. And then later you combine decision of multiple definition using the weighted voting, the bargain, or whatever options you are going to have. So you see you have the training data, which you partition it to data 1, data 2, up to data M. Depending, M is the number of ensemble you want to be, number of base learners, sorry. Number of base learners you want to be, the individual that you want to combine later. So your M can be 3, it can be 5, can be any number. So bring in the algorithm. The algorithm now, which we call the learner. The algorithm, these are the algorithm. This could be KNN. This will be SVM. This will be neural network, depending. So when you have different algorithms, then your data could be the same. But if the algorithms are the same, then it's better your data is different. And your data can be different and also your algorithm different. That's why it's a kind of, you keep generating. The idea is we want to generate as many models as possible that is looking at the problem from different point of view, so that we don't want to lose any information in the data. So with data smartly combined with the algorithm, you generate models. Then different model now, you can have the model combiner, like which I mentioned. It could be bargain, which is majority voting. So it could be boosting, where we give more priority, more votes to the guy we give more vote to the model that achieves more accuracy. And then we can also have the one I call stacking. So where we are going to, instead of doing, we are not going to do majority or whatever voting, we will bring in another algorithm here to come and help us do the combination. Now, so this is the final model that we have. Now, another very important concept I will mention, because when you try to modify your data set, you might need to play with your data, create different versions of your data. That's why we talk about sampling techniques and concept to be used. You see, in sampling, we have 3 major types of sampling. We have the simple random sampling. Here, there's an equal probability of selecting any item. We just randomly partition the data. Some will become training set here, testing set, training set, testing set. The other one is the sampling without replacement. Each item is selected, it is removed from the population. Once you select an item to be part of the training set, you remove it from the population. It means it cannot be selected twice. While we have sampling with replacement, objects are not removed from the population as you are selecting them. Therefore, same object can be picked more than one. That is sampling with replacement. Any of them is allowed. However, the simple random sampling method is highly recommended, but others also are good, depending on the kind of model you want to build, the kind of ensemble you want to build. So we're going to be referring back to any of these 3 as we move on, inshallah, in discussing different ensemble method principles. So it's kind of a review what we've done. So the concept of model, we keep mentioning model. So when you have the model, you have to pay attention to the training error and the generalization. Generalization is the most important thing I told you. That is the testing error or the validation error. So we don't look at the training error. If the training error, it can be confusing to you. Maybe there's overfitting or underfitting or what have you. So what we are looking for, we need individual models to have as better performance as possible. You can make them to be better before you even combine them. So we don't want you to say, okay, I just want to combine because I'm doing ensemble. I'm getting there's a model 1, it's having 25% accuracy. Inshallah, it will perform. I'm going to use it in an ensemble. Don't just because of ensemble, you develop bad model. Make it at least as best as you can, and then let them come. Otherwise, that's why they say 2 good heads are better than 1, not just any heads, because you can't just bring in any model. They might disrupt the ensemble system you are building. Maybe it doesn't even understand the data all along. Now, So you have of course, you have the training data. You always check it to make sure it is working fine. So where you are going to have the training error to check what is the error that the training is producing. And then the testing error is what we really need. Is it going fine? Is it reasonable? If the error is really high, we can use such model in the boosting type that will give more weight to the output of such base learner compared to the others. And also we discussed the concept of underfitting, overfitting. So you need to know where to stop. That is when you are building individual models that you are going to combine. Because Ensemble is you first develop individual models, as many as you want, 3, 5, 7. It can be as much as possible. And then you want to make sure that those you are going to bring into the group, don't bring a failed classifier, don't bring them in, a failed model that is underfitting or overfitting. We don't need it. They'll create chaos in the ensemble you want to develop. So remember this underfitting. If you train carelessly, you end up stopping here. That is underfitting. If you are too greedy, you keep improving the testing accuracy until you end up having very bad result. That is overfitting. So we try to stay at the middle. So this is the idea. So in a data-rich situation, the best approach to both model selection and model assessment is to randomly divide the data set into training set and then fit the model. This is generally, if the data is rich, you have so much data there, just divide it into 2 or 3, training set, testing set, and validation set. But if your data is very few, then you go for 10-fold cross-validation. Because in that case, dividing is not possible. You have only 15 samples. How are you going to divide into 2? So we go into cross-validation idea. But if your data is huge, for sure, we go for the holdout method, which we call the dividing into training and testing set. Now, further visualization of the rationale or rationalization, justification of ensemble. So the no free lunch theorem says that there's no algorithm that is always the most accurate in all situations. So we want to take advantage of this. So in that case, you generate a group of base learners, which when combined has higher accuracy. This is the idea, that when you are looking at data, when data is sent to you, your machine learning look at it from this point of view of these people. They try to see that, look at this man is holding an elephant. He said that an elephant is a big snake. This is what he can visualize because it's holding, that model is able to understand the trunk of the elephant only. That's what the data, that's what your algorithm can, this guy is standing for algorithm. It's maybe KNN1. This man is saying, actually, no. He's arguing with this guy. He said, no, it is a tree stump because it's only able to understand the leg. It's catching the leg. Meanwhile, this one is saying, what are you saying? It is like a sheet of leather because it's able to touch this side. So this man is saying, you are all wrong. It is actually like a little furry mouse. So because it's touching the tail of the elephant, he said, oh, this is a little furry mouse. And this is the life, this is kind of life. You know, in life, we look at things from different angles. You see? That's why we don't always want people to have the same opinion like us. It's not possible. And this is one of the problems of human relationship. Someone wants everybody to have the same opinion like him or her. It's not possible because his brain is looking at it from another angle. You are looking at it from another angle. We should allow this kind of thing in our day-to-day activity. Sit them together, discuss. You come to a round table and you come to an agree point. So you can see that these guys, some people say they are blind in some other presentation, that this is what they can touch and see. And this is how the algorithm works, machine learning algorithm. It's like a blind stuff searching for useful information inside your data. So sometimes they can miss some information. So imagine this is a model 1, model 2, model 3, model 4. Look at them. They are all seeing different things. So we need more. Another one need to come and study this place, what of this part of the body, so that later, when we want to really recognize, we can carry out actual recognition. So this is the idea. So you can see this is model 1, model 2, model 3, model 4, model 5, model 6. You can train more. This is unknown distribution. This is your data. Your data is so big like elephant that we don't understand the underlying principle of your data. We don't understand the distribution pattern. So let the model, let the algorithm learn from them. Each of them will learn and produce model. This is what I can see. So later, when we are going to decide, okay, what is this? This one will say, it looks like this is yes. This one say yes. This one say no, I disagree. This one say yes. We can them either use boosting, bagging, or stacking, whichever method. So what we are saying is that in real life, when you use different models on the same data, they will look at your data from different angles, and they can give you better output, inshallah. So the ensemble will give the global picture. This is the summary. Ensemble gives the global picture. So that at the end of the day, when you're going to combine them together, you are not looking at the opinion of one person or one model, you are looking at the opinion of a group of people. See, you have a global picture, which is better than individual picture. And this is what we get when we bring experts to the table. Let them discuss. This is what I see. This is what I see. What if we do it this way? Then by then, you are going to find, oh, everybody will agree, oh, this is the best way to do it. You use little from expert 1, a little from expert 3, little from expert 4. We bring them together, we get better outcome. So this is how it works. You say this is random forest, which is one model developed. This is another logistic regression-based model, KNN. This one is saying there's a fraud there. This one is saying there's no fraud. This one is saying not a fraud, a classification. So we vote. This is a voting classifier, a super classifier. Okay, we count them. One person said it's a fraud. This one said not a fraud. 2, majority carried the vote. So we say the output is not a fraud. So we are taking decision based on the opinion of 3 stuff here now. Now, so let's say that suppose you want to buy a laptop. You may want to ask one of your friends to rate the laptop for you. Another way could be by asking 5 colleagues of yours to rate the laptop. How about asking 50 people to rate the laptops? See, this as ensemble ideas. So the response in this case will be more generalized and diverse since you have people with different set of skills. This is another thing. See, when you have those 3 your friends to tell your idea, because they love you, they are with you, they are likely going to give you what you would like to hear. This thing happens a lot. This is why in Ensemble, we encourage you to develop diversified base learners. Train KNN, train SVM, train different type of models. Let them tell you their own idea about your data. So don't just talk to your own friend. They are sincere to you, but they are this guy will like this. They always think what you will like. But talk to people who doesn't know your preference. Let them recommend laptop to you based on their own experience. You might get better outcome compared to when you're only talking to your people. And that is the group, the power of people. The more you are, actually, the better. So we said a diverse group of people are likely to make better decisions as compared to individuals. You can see a diverse group of people, not just group of people. If we are a group of people, but we are having the same orientation, we are likely to have a limited decision-making capability. But we have people from different backgrounds. I have minor engineer here now. I have economists here. I have mathematician here. I have medical practitioner here. So many people in this group now. So if you want to make decision, hopefully we come up with very robust decision in our hardcore. So the diversification in machine learning is achieved by a technique called the ensemble learning. This is the idea. So machine learning says, okay, we also need to diversify. We need to take opinion from different machine learning algorithm, and then we can reach better outcome, just like we do in our day-to-day activity. So you see that an ensemble is a set of classifier whose individual decisions are combined in some way to classify new examples. It predicts class labels on previously unseen record by aggregating predictions made by multiple classifiers. And the main principle behind ensemble modeling is to group weak learners together to form strong learners. The idea is that as individuals, we are weak. The same thing. You train SVM, even though it's a very strong classifier, but as an individual, it is considered weak. And the same thing with us. Like we used to say, like when you see a snake, when a snake goes about, if the snake goes about, if a group of snakes go about in group, nobody can challenge them. But because they go as individual, that is why even a small boy can take something and kill a small snake. So, because if they go in group, they become very strong, intimidating. That is the idea about machine learning ensemble. that every machine learning ensemble is considered weak. So machine learning algorithm is considered weak as an individual. Just like we are also weak as individuals. But when we come together as a group, even as a country, when you come together as a group, you become stronger. We all know this fact. So using multiple learning algorithms together for the same task can ensure better prediction than individual learning algorithm we ever do. We have a lot of examples we can continue to give that has demonstrated this. So in essence, when you go for ensemble method, it's a combination of multiple and diverse models. Each model in the ensemble makes a prediction, and the final prediction is determined by majority vote among the model. So look at this one. We have the input sample, model A, model B, model C. This is the output. You vote here to get the final result for the ensemble. Yeah, so we will stop on this example for the day, inshallah. So we are going to continue next time. Look at this example, everybody. So this is a model that you learn. You have trained a model. This is the reality. Reality means the output. This is the output they give you. This is original, the answer. They give you this answer originally. Now, this is model 1. This is model 1. Model 1, model 2, model 3. I trained 5 models now. Now I trained 5 algorithms to produce 5 models. Now, model 1 is saying that this one, this is the answer here. This is cloudy, which is correct. There's no cloudy here. Children can play outside here. This one got it wrong. 1, 2, 3, 4. 4 correct, 3 wrong. Another model got this right, got this wrong. You can see the advantage is that what this model is mistaken for, this one is getting it right. See, what this model is getting right, this one got it wrong. You can see individual ones are making their different mistakes. This is the idea of ensemble. Now, you can see that no single model got 100% accuracy. No, this one is having 1, 2, 3, 3 mistakes. 1, 2, 3, 3 mistakes. 1, 2, 3, 3 mistakes. 1, 2, 2 mistakes. These are the only fewer mistakes. 1, 2, 2 mistakes. Every one of them has at least minimum of 2 mistakes. We are talking of out of, that is 1, 2, 3, 4, 5, 6, 7. Maybe percentage, we're talking of maybe this one is like maybe 70% accuracy. This one is maybe 70% accuracy. This one is 70%. This one is 80%, something like that. But then let us combine them together. You see that they're going to get us excellent results. Look at this one. We're going to, what is the output of this guy? This one say cloudy, 1, cloudy, cloudy, cloudy. 4 cloudy against 1 non-cloudy. So this one is only one that is wrong. 4 against 1, we go for cloudy, which is correct as the original output. Look here, 1, 2, 1, 2, 3. 3 against 2, we go for 3. 2 against 3, we go for the 3. You can see that majority carries the vote. At the end of the day, this is correct because it's the same thing like the original answer given to us. Correct, 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 correct. We get 100%. This is a practical demonstration of ensemble. Even though there's no single individual model that achieves, there's even no 90% accuracy, by the way. If you do the calculation here, no one got 90%, but now we are getting 100% with 5 of them. That is the power of ensemble that we are mentioning. That when you have individual models that are relatively diverse, independent of themselves, they make mistakes, that's fine. But when we combine them together, they vote to choose the best results, they end up having excellent results. So this is a demonstration here. You can see a maximum here, we got like 80 or 85%, but now we're having 100% accuracy. So that is an example of a weather forecasting ensemble system. So in your own application area in engineering, you can also try this out. In which case, individual model might get stuck as maximum of 80%. Don't worry. Train many of them, combine them together, let them vote, and if it is regression problem, you find the average of their results, and then hopefully you get better results. A lot of demonstrated real-life example that have shown that with Ensemble, you can get better and excellent results. So I think this is where we're going to stop for today, inshallah. So we have any question? Okay.
Yes.
Okay, Mr. Mubarak. Yeah. Further. I'm listening. Okay. Okay, Dr. Musa.
Okay, my question.
Okay.
In the Ensemble method, we've been using a classifier as an sample.
Yeah.
How do we use it for regression method to generate a regression equation? How are we going to combine all the model to generate one single regression equation?
Okay, thank you very much, Prof. See, the concept of generating ensemble, the concept of generating regression equation from machine learning is a kind of, it's still a very controversial area, because there are lots of machine learning experts that believe that generating regression equation from machine learning is reducing it back to a regression equation as Leah that we started with. You see, it's reducing it back to regression equation. There's still the difference of opinion. People believe that no, once you train a model, because training a model involves using data. So what we have is a software that we're going to deploy. You bring in your data, you input your data. Of course, there are some algorithms that support it. They're very simple. You can easily plug in a data into a particular set of kind of equation. However, when we go to Ensemble, so we are still coming back to that. One of the challenges of Ensemble is it distorts the clarity of the process. So that one has to be clear. We are coming to mention that later. That's the major disadvantage of Ensemble. When you go to a client, okay, the client wants to see the way it works. That's why I always recommend for my student to use decision tree. In decision tree, you can easily explain it to people. This is how it works. This is how it works. K-nearest neighbor also is very easy to explain. Support vector machine, you need to have some mathematical background before you can understand what is going on there. Neural network also, some people call it black box, but there are attempts of recent to make it white, to try to make it, to white it out so that people can understand what is going on. But some numbers might still not be reasonable to some people. But however, when you come to Ensemble, it distorts all these things we're talking about, Prof. See, because now imagine you train 105 base learners, and now you combine them together by voting. You know, voting is involved. Either you're going to do regression and whatever, either you're going to do a kind of, if it is regression equation, regression problem, you're going to do the weighted averaging. Okay, this one is predicting the age of the student to be 23.4. This one is predicted to be 25.5. Okay, we do the average together and get the final age. So in that case, you are thinking of having, if you can have a regression equation for one of them, then you can produce regression equation for all the classifiers you have trained, all the regression equation that you can get them. Once we get the regression equation for like maybe 107, then whatever output you have in that regression equation, then you are going to also find the average, just like you did in the Ensemble. I think most simple, simplified way we can present such a thing. But like I said, when we train models, reducing it totally to regression equation, a lot of things might get lost along the way. There are some models that support that, but there are some algorithms that might not really work well when we reduce them to regression equation. I hope I answer your question.
Yes.
Okay.
Now my question is, at what stage do we actually give this assembly thought? Will it be a function of low accuracy that we observe? That we not think, okay, let's just use a sample.
Okay, thank you very much. So we're coming to that. where we're going to discuss the technical reasons that there are some reasons that when you see your data, you know that the best way to make good use of this data is to go for Ensemble. For example, you suddenly saw that your data is having like 500 features. And the expert said, these features, we don't want you to ignore these features. They're very important features. But then training a single model with 500 features is too much. The computational complexity might be inhibitive. You might not be able to do it better or to even complete in the acceptable time limit. So in that case, can't we divide those features into groups from 1 to 10, from 11 to 20, from 20? So we keep each group, we use it to train a particular classifier. And in bagging, you can train as individual. We have a team of students working together, like 50 students working with me. I can ask the first student to train 2 of them, another student 2 of them. It means within a few hours, all of us can train like 50 times 3. We can treat like 151 models. So we come to that quickly, like a kind of, there's a Kaggle kind of, there's this site called Kaggle. Regularly, they give out kind of competition. So I gave out the site last week. They give competition out. There's a competition out now. If you have some students who are interested, you can gather students together. Maya looking at the data, we said, we don't want to waste our time. Let's go for Ensemble straight. You see, you train these, 3 of these, 3 of these, 3 of these, because the data set itself, based on my experience there, I know that maybe Ensemble will be better. So in that case, there's something you can look into your data. We are going to discuss them later. That will give you the feeling that no, Ensemble should be the best. However, the basic intuition is if your accuracy is not improving, because except in very few cases, I just mentioned one of them, when the number of features are just too much. And feature selection is not an option because the expert said, no, every feature is good. Maybe you calculated the feature important. All of them are showing that they are important. In that case, you have no feature to kick out. In that case, you have to try to see how you can take advantage of those good features. However, the basic thing like this example here, we are made to realize that we are getting like 50-something% accuracy, 57% accuracy, for example, 57% accuracy. So this is too low. We try whatever we can do, we couldn't improve it further. That is a potential candidate for Ensemble because 57% accuracy is very low. But then Ensemble now gave you the opportunity that don't despair. Maybe this one will be like 67. None of them is even up to 70. So then we go here and say, okay. By the time we combine them, we find out that even though none of them achieve 70% accuracy, we are getting 100% in the Ensemble. So low accuracy of the individual classifier, like I tried to develop support vector machine, which I trust most. From my experience so far, it's always worked for very few data samples. I got only 85% accuracy. And it's not enough for what we are looking for. People worked before they got 87. Now we're getting 85. So I need to move further and get something better. In that case, I will have to start considering Ensemble. So lack of ability to reach the expected accuracy is one of the reasons for using Ensemble. So if you already achieved 97% accuracy, somebody say, I want to achieve 98. I say, are you going to start developing Ensemble because of just 1%? If you think it's worth it, you go ahead. But if you think 1% improvement, just to spend another 2 days, no, it doesn't worth it. So that's why it depends. But if you're getting accuracy like 57, 67, for sure, it's worth it to go for Ensemble and try to get better results. I hope that clarifies.